Hello everyone, so this is the fourth video in our playlist, and in this video we're gonna look at a question which tells us that we're given a cylindrical cup of radius r and height h is filled with water to a level of h0, and we're asked to derive an expression for the maximum angular frequency of omega. The cup can be rotated without spilling the contents. Okay, before approaching to the question, we're gonna draw a diagram to see what's really happening in our question. So we're gonna start by drawing a cylindrical cup of a radius r, right? And it's gonna have a height of big H, and then it's filled with water to a level of H0, right? And we are told that it is rotating with angular velocity of omega. And what's going to happen in our question, as we know, the water level is going to be something similar to this one, okay? Like this, right? And then, so if I'm going to do this, so it's gonna decrease but by some level, right? And this part is gonna increase. So in this question, we're asked to find the maximum angular frequency. Angular frequency, we can rotate the cup so that we can have, we do not spill any of the contents. Okay, so this part is gonna be consisting of air, right? And this is going to be the bottom part of our we can say that this is going to be the distance. It decreases, the height it decreases, and we can kind of mark it as d, and this is still going to be our radius. And we're going to say that at specific point when radius is equal to 0, our pressure is going to be equal to 0, okay? And then as we know the equation for the pressure when the object is being rotated in a turntable. So it is pressure is equal to the initial pressure plus the density times omega squared, which is the angular frequency squared, multiplied by radius squared minus initial radius squared. And our r is equal to 0 at this point, and our pressure, initial pressure, is also going to be equal to 0. So a new equation we're going to have is going to be the density multiplied by angular frequency squared and r squared, because our initial radius is going to be 0 at this point. Okay, so and then if we just consider this point, let's say if we're going to consider this point, specific point. So this should have some height, right? And as we know, at this point, the point is going to have only one pressure. And which means the pressure we determine from the width, from the radius, should be equal to the pressure we determine from the height. So as we know, from physics, the pressure, like as we go down to the water, is going to be equal to the rho g h, which is going to be the density multiplied the gravitational acceleration times the height, and that should be equal to our equation that we just derived. Okay, so I'm going to write that equation, what I just said. So our pressure determined from height should be equal to our pressure determined from the radius, right? So now we can see that the densities are going to cancel out each other, and the equation we're going to have for height is going to be the angular frequency squared radius squared over g. So, and yes, so this is how we determine the height of water at any specific radius. So it's how the water raises as we rotate it. And then So when we look back to our diagram, we know that the water has some volume here, right? And it's going to decrease by some amount, by some distance, and this volume here should be equal to this volume here if no water is spilled out from the cylinder. So what we can do here is, so we can make those each volumes equal to each other, so that we are going to determine the point of our frequency so that it's going to be equal to each other, so that no water is leaving our cylinder. So for this part, so the first, before we're rotating, how we find the volume is just going to be the circumference multiplied by the height, right? So like by this distance. So initially we said this is going to be our d, right? So we're going to just multiply pi square r d, and this is going to be the volume of our water before it starts to rotate. And for the after rotation, what we're going to do is we're going to look at the cylinder from above, and we have to find the volume by very small distances. So, and what we're going to do we're going to integrate as a cylinder. So we're going to consider very small amount, and then we're going to rotate from r is equal to 0 to r is equal to big R, so that we find the volume of water at the shaded region. Okay? So, and then, so as I said, for that part, it's going to be, so it's going to be like 2 pi r, it's going to be the circumference, right? No, yeah, it's going to be the circumference. 2 pi r multiplied by this small distance here. I'm going to say that it's going to be dr. It's because that's the small radius we're considering, and it's also multiplied by height, right? So it is circumference of a circle multiplied by the thickness, as we can refer to it, which is dr, and multiplied by height. And this is going to be our volume at this point. But if you want to find the total volume when it starts to rotate, we're going to take an integral from 0 to r. And what we told before is these volumes should be equal to each other. So what I'm going to write now is I'm going to do, so pi r, oh, here I noticed the mistake. So it is not pi squared r, but pi r squared. So pi r squared d is going to be equal to the integral from 0 to r 2 pi r h dr, right? Okay, so I'm gonna change the formulation of our equation a bit. So I'm gonna leave the left hand side as it is, and for the right hand side, I'm gonna replace this h by the equation we already determined. Okay, so just to see what happens. 2 pi r times omega squared r squared over g. And then, and don't forget the dr. If I'm gonna pull out all the constants from our question, it's gonna be 2 pi omega squared over g, and from 0 to r cubed dr. And as we notice, pi is going to cancel. Oh, I think I forgot something. Oh, yeah. Here I forgot to divide this equation by 2 because the pressure is going to be the 2 times less than here. Okay. And which means I'm going to have 2 here and I'm going to have 2 here. So which means when I have 2 here, these 2 is going to cancel out. Okay, let me correct it here, correct it here, correct it here. Okay, then what the new equation we have is gonna be, so this was big R. Yep. Okay, so it's gonna be R squared D is gonna equal omega squared over G, and I'm gonna take the integral. So it's gonna be R squared over R to the 4th over 4 from 0 to R. And at 0 it's going to be 0, so the equation we're going to have is going to be D is equal RD omega squared over G times big R over 4. Okay, and oops, R to the 4th. And then the R is going to cancel, so R squared is going to cancel with R4, so we're going to be left with R4 on the right hand side. And how I can write the equation for D is, it's going to be omega, angular frequency squared, the radius squared over 4G. And this is how we determine the distance, the level of water, how the level of water decreases as we start to rotate it. So this is the equation we're going to need. Okay, let's go back to the diagram and see what's happening. So we're setting up in a question where, given that we should not spill any of the content, right? So which means the initial height, so we have some initial height, right? So then it's going to decrease by the distance of D, and here it's going to increase by the distance of H. So the H is going to be measured from here by the level of water it decreases. And so if we subtract our decrease from our initial height and add our increase of liquid level, it should equal to the big H, which is the height of a cylinder. So how I can write that equation is, so height of a cylinder should be equal to the initial height of a cylinder, initial height of a liquid minus D, which is how the liquid level decreases, plus H. And I'm going to substitute this variable with this equation, and I'm going to substitute this variable from the equation we calculated in the beginning with this one. Okay, so what I'm going to have is the big H, okay, my handwriting is not the best, equals H0 minus D, which is angular frequency squared R squared over 4G, plus H, which is going to be omega squared R squared over 2G. And R here is going to be the big R. And then, so if we look at this part of our equation, it's going to cancel. So if we simplify it, it's going to be equal to H0 plus omega squared R squared over 4G. And then we are solving for the angular frequency. So in the question, we're asked to find the angular frequency. The cup can be rotated. So we just have to make the omega the subject of our equation. So what we're going to do is, it's going to be 8 minus HO omega square R square over 4G. And the omega squared is going to be equal to 4gh minus initial height of a cup minus the height of a liquid level over r squared. So in order to find the angular frequency, we're just going to take a square root of it. So it's going to be 4g, 4 times the gravitational acceleration minus height of a cup minus initial height of a liquid level over the radius of a cup squared. So this is how we can model our model of a cylindrical cup that is being rotated, and this is going to be, so this is equation represents the maximum angular frequency we can have so that we do not spill any of the contents. Thank you for your attention.